This is the second part of this derivation of the standard error of beta hat 1. So in the first part, I showed that if you start with this, this holds. And now in the second part, I'm going to start here and show that this holds. And this is also called, the expectation of beta hat 1 being beta 1 is also called the proof of beta hat 1 being unbiased. Beta hat 1 is unbiased. Its distribution is centered on the true value, the true relationship of how x affects y. So that's the proof for this video. So let's say, here we are. So I'm going to start here. And I want to show that beta hat 1 is unbiased and that this holds. So I'll also use this rule a little bit later on. I just wrote it down because it's kind of time consuming to write that. So my first step is I'm going to simplify this a little bit by adding a new variable wi. I'm going to let wi be defined as xi minus x bar over sum I xi minus x bar squared. And I use the letter W because W refers to the weight. It's the weight of the observation. It's how important the observation is in determining the parameter values. So now with this new variable, we can say beta hat 1 is just beta 1 plus sum I wi ui. And now, well, it's a lot simpler, and my next move is going to take expectations of both sides of this equation. So I'll have expectation beta hat 1 is the expectation of beta 1. Of course, beta 1 is just a number. So the expectation of a number is just the number, so I'll just write beta 1. Plus, and then we have the expectation of this term, sum I wi ui. And we can swap the sum and the expectation because the expectation of a sum of a bunch of things is just the sum of those expectations. So beta 1 plus sum I expectation wi ui. And the idea is we want to argue why this is 0. Because if that's 0, then we get that the expectation of beta hat 1 is beta 1, which is what we wanted to show. But we're a little bit stuck right now, just using these unconditional expectations. Now we want to bring in this rule. And I'm going to talk a lot more about this rule, this conditional expectations rule, when we talk about exogeneity and admitted variable bias. But for now, I'll just show you how it works. So we have an unconditional expectation here, and we're stuck. We can't move forward. But the idea is that if we can take a conditional expectation of wi ui conditioned on something, and if we can show that that is a constant, then we know that the unconditional expectation wi ui, is that same constant, and hopefully 0. So let me see. We're going to take a conditional expectation of wi ui. Wi ui conditioned on big X, which is xi in all observations, for all I guess. So if we can show that this conditional expectation is a constant, then we know that the unconditional expectation wi ui, is that same constant. Now, if we condition on something like x, and because we know wi is a function of only x's, we treat wi as a constant. Because we've conditioned on it, its known value, we can bring that wi outside of the expectation. So this just becomes wi expectation ui conditioned on x. And now, this should look familiar. This is our big assumption. Exogeneity. assuming that the expectation of ui conditioned on x is 0, that's called exogeneity. And we'll talk about violations of that assumption when we talk about omitted variable bias. But for now, just recognize this is where this big assumption comes in. If we assume that this thing is 0, what do we get? We get that this thing is 0. We've shown, therefore, that the conditional expectation of wi ui is 0. And so we know that the unconditional expectation of wi ui is also 0. So we get that the expectation of beta hat 1 is beta 1 plus sum I 0. We can sum 0 n number of times, it's still 0. And so we're left with that the expectation of beta hat 1 is beta 1. And that's the proof for this part.